to stay on time because this is going to be a debate type of presentation. I'm just going to get started. So I'll first introduce myself. I'm Diana Dragomir, and I'm a postdoc here working on observations of exoplanets. And while I do the rest, please take a look at the ballots on your chairs and think about and begin to vote on the question that I'm about to say. So that is, by the end of 2042, remote sensing will reveal evidence of extant life on an exoplanet. Quick definitions. On the white one, yes, the pre-debate vote. Keep the other one, don't throw it up. So by remote sensing, we mean, I'm just going to read it off so it's clear, we mean that we do not actually have to visit, but that the evidence will be pieced from spectroscopy or radio waves. And extant life means we are not just detecting the fossil evidence of life, but that there are actually living things still living on the planet. Okay? So while you're voting, I'm going to introduce the panels. So I'm going to start on the... Only vote on the white. Okay? And keep the blue for afterwards.
Anyone missing a ballot?
We'll vote again at the end.
Sorry, life could be like single cell organisms?
I'm sorry, what?
Life could be like single cell, super simple organisms? Or...
Yes.
Did it have to be water-based?
No. Just light.
You're fine. What's five? Gravitational waves will count as light.
This is why you need to vote again, okay?
How many times did you vote?
Alright, so I'm just going to go ahead and introduce the panel. So on the pro side, we have, I'm going to start, hold on, start the other way. So Laura Kreiber, who's an NSF graduate fellow here in astronomy. And then we have Leslie Rogers, who is an assistant professor, brand new, starting next year, and currently at UC Berkeley. And then we have Professor Dorian Abbott, who is in the Geophysical Sciences department. And then on the com side, I'm going to start at the far end. So we have Jacob Bean, who is an assistant professor in astronomy. And then we have Dan Fabergy, who is also an assistant professor in astronomy. And then we have Edwin Kite, who is an assistant professor in geophysical sciences. Okay? So the format will be 15 minutes for the pro side, and then 15 minutes for the con side. And then the pro side gets a 2-minute rebuttal, and then the con side gets a 2-minute rebuttal, and afterwards we will have questions. Okay? And each side will get a 2-minute warning. You may begin.
Okay, I hope everyone's ready. So I'm going to read the proposition again. By the end of 2042, remote sensing will reveal evidence of extant life on an exoplanet. So first I want to take a second to just define what that means. What the
That's a drink.
like this way. Ooh. So first of all, this came up, some of the questions people were asking. We're not talking about intelligent life. So life is any type of life. And the second point that I think we need to get right out front is that evidence of life is not the same thing as absolute 100% proof for life. And so on our side, we're going to give you some examples of things that we think could be characterized as evidence of life, and then you can judge whether you think those things are realistic and whether you think we're going to be able to detect them in the next 27 years. So what we're going to argue, the three of us, is number one, what I'm going to argue is that life is common in the galaxy. Number two, that life produces biosignatures, so that life changes the atmosphere of a planet in a way that we can detect. And number three, that we'll actually detect these biosignatures by 2042. So that's sort of the plan on our side. Okay, so first of all, life is common. That's what I'm going to argue right now. So almost no one, I think, would argue that simple life, that microbial life is uncommon in the universe. There's a whole group of people that we call rare earthers who think that life, that Earth is a very rare, the particular conditions that led to us on Earth are rare, and that complex life will be uncommon in the galaxy and the universe, so that maybe Earth is the only example of a planet that produced complex animal intelligent life that can produce radio telescopes and things like that in the whole galaxy. But even those people acknowledge that simple life, microbial type life, is common throughout the universe and may even be present elsewhere in our solar system. And I'm going to give you 5 reasons why that is probably true. And you can make your mind up whether you think they're convincing or not. So number 1, we now know from the Kepler mission that there are tens of billions of Earth-like planets in our galaxy. So something like 1 per star. When you look up and you see all the stars, and all the stars that you don't see, there's about 1 Earth-like planet out there per star, which means a planet about Earth size, a terrestrial planet, somewhere in a distance from the star so that it can have liquid water at its surface. So it's close to the order of 1 per star. So there's a ton of potential environments for life, even if we use a restrictive definition of a potential environment, and we're looking for something just like Earth. Number 2, the raw material for life is everywhere in the universe. So if we just start with water, which all Earth life needs, hydrogen and oxygen are really common atoms, and they frequently combine to make water, and we find them in other solar systems and all over the place on planets and moons. And number 2, organic material, carbon and hydrogen bonds together, is common. It can be found in interstellar space, on asteroids, and on other moons and on other planets. So the stuff to make life is very common. Number 3, as far as we can tell, life arose on Earth about as soon as it could have arisen. So Earth is about 4.5 billion years old, and the late heavy bombardment ended at about 3.8 billion years ago. And the earliest geochemical evidence that we have for life occurs at 4.1 billion years ago. And the earliest nearly certain microfossils are 3.5 billion years ago. And after that, there's a 3 billion year gap until we start getting complex life. And what that indicates to me is that the early origin of life wasn't necessary to get increased complexity and to get to us. So the fact that we see evidence early on life, or of life early on Earth, isn't biased by the fact that we're here, because there was this huge gap where life was simple. And so it is an argument that as soon as the conditions were primed for life on Earth, that it almost immediately evolved. That's an argument that if you get those conditions elsewhere, then you're probably going to get simple life. Number 4, on Earth, life can thrive in totally wild, diverse, and extreme environments. So, for example, kilometers below Earth's surface, in hot springs, in deep sea vents, and in Antarctica. And there's a huge number of planets, moons, and other sorts of objects in the galaxy that are going to experience these conditions, since they're in such a broad range. And the 5th, the final reason I'm going to talk about, is that life has been hugely resilient on Earth. So once it arises, it's really hard to get rid of it. So on Earth, we've had huge impacts. We've had hothouse climates, large igneous provinces, which are these big belches. Okay, I almost stopped. These big belches of toxic gases that can dominate the atmosphere for millions of years. And we've had snowball Earth events. And even when these things have caused mass extinctions of animal life, as far as we can tell, microbial life just cruised right through. And so if life evolves somewhere, it's likely that the various annoying things that the galaxy does to it will extinguish it.
So life, even simple life, will modify its environment. So life needs energy to stay alive, to build biomass. And to get that energy, it leverages light and chemical potential energy. So generically, this involves consuming some reagents, extracting energy, and generating some modified products. So no matter how green these aliens are, they will inevitably pollute. So one pathway moving forward towards the detection of extant life by 2042 on an exoplanet will be the identification in the atmosphere of the planet of a gaseous pollutant produced by life, or a biosignature gas. The question is then, will life pollute sufficiently to be detectable, and will their pollution be distinguishable as a consequence of life as opposed to some abiotic process? So on the first issue of whether life will produce enough biosignature actually evaluate this semi-quantitatively. So given telescope observing capabilities, that essentially sets a minimum detectable concentration of biosignature gas in the planet atmosphere. Then with some model of the abiotic sources and sinks for that gas in a planet atmosphere, we can estimate what biotic source flux in terms of molecules per second per unit surface area on the planet is required to achieve that detectable concentration. And then that can then be related to a biomass per surface density required, which we can then assess relative to our intuition here on Earth to see if that's crazy or not. So this type of reasoning is being applied to vet proposed theoretical biosignatures and could eventually also be applied to assess future candidate biosignature detections. Now on the second issue of attributing biosignatures to biotic or abiotic sources, it's true, many of the gases that life produces will be ambiguous, like water, methane, carbon dioxide. Those are created by geophysical processes and are naturally found without life. An ideal biosignature will be a molecule that does not exist naturally in the planet's atmosphere, and yet when produced by life is in the gas phase in the atmosphere and not dissolved in the oceans or deposited on the ground. And it will also not be created by geochemical or geophysical processes, will not be rapidly produced or quickly destroyed by photochemistry, and further, it needs to have a strong spectral signature so that it can be detected. So a few examples. Here on the Earth, molecular oxygen, O2, is the most robust biosignature gas. So O2 is produced in abundance by photosynthesis. It has no known photochemical or geochemical sources that could yield such large quantities, and it also has electronic transitions in the visible that could be used to detect it. A second example, we can turn to rocky planets with hydrogen-dominated atmospheres. So Kepler has shown that it's actually common for planets that are even just a few Earth masses to retain a hydrogen envelope. And so in these reducing conditions, ammonia is perhaps the best potential biosignature gas. So like oxygen in Earth's atmosphere, there are no kind of photochemical or geochemical false positives that could produce large concentrations. Ammonia also has a short photochemical lifetime, so if we were to observe it in a hydrogen-rich exoplanet, it would mean that it's currently being produced and replenished, and ammonia is spectrally active in the infrared. And based on some theoretical estimates, an Earth mass planet with a 1 bar hydrogen-nitrogen atmosphere would need just a modest 0.1 grams per meter squared biomass to sustain a detectable ammonia signature in its atmosphere. And for context, that's about 1/1000th of the biomass of photosynthetic bacteria in the Earth's ocean. So in addition to these two examples, there's a wide range of other biosignature gases in the literature that have been proposed. They're with varying levels of robustness, and they're more subject to false positives. But even if the initial detection of a biosignature gas on an exoplanet is not a triumphant 100% certain slam dunk by 2042, the exoplanet field by then will have developed a framework to probabilistically assess the likelihood that a molecule in a given atmosphere is attributable to life. And as Laura will argue next, we will have the technical ability to detect biosignatures that have a significant non-zero probability of being attributed to life.
Okay, so the million-dollar question is, will we actually be able to detect these biosignatures by 2042? Actually, perhaps it's more like the $10 billion question. In order to detect biosignatures, we need two things. First, we need a sample of nearby Earth-like planets whose atmospheres we can study. And second, we're going to need a big, huge space telescope to be able to study those atmospheres. And as for the first part, it's basically a done deal. We know from the Kepler Space Telescope roughly what the occurrence rate of Earth-like planets is. The best current estimates are that the nearest transiting Earth-like planet is within 20 parsecs of the Earth. Even just last week, there was an announcement of a planet 16% larger than the Earth, 12 parsecs away from us. And so we'll have a sample of planets to choose from by 2042. That will not be the limiting factor. The second part of the question is more challenging. Will we actually be able to observe the atmospheres of these planets, measure high-quality spectra in order to detect biosignatures? And so I thought I would just start by giving a snapshot of the current state of the art, which is that the main technique that we use is called transmission spectroscopy, and the idea is that for planets that are transiting in front of their host stars, periodically passing between the star and us, when the planet is in its transit, a small fraction of the stellar flux passes through the planet's atmosphere and can be absorbed by molecules there. And so by measuring a transmission spectrum for an exoplanet, we can infer its atmospheric composition and its temperature. And this has been used to great success for hot Jupiter-sized planets. And we've even begun making inroads into the atmospheres of smaller and cooler exoplanets. So disclaimer, this is going to work, but I'll talk about it anyway because it's relevant. For the super-Earth, JJ1214b, which is just 2.5 times the size of the Earth, with an equilibrium temperature of about 500 Kelvin, so a little bit bigger and a little bit hotter than the Earth. We were able to make a measurement of its transmission spectrum that is sufficiently precise to detect an Earth-like atmospheric composition on the planet. That is to say, if the atmosphere were made of nitrogen with trace amounts of water, we would have detected that. And that's not actually what we found, but the point is that the capability of making the measurement is there. And in the future, looking forward to JWST, that will allow us to make even more precise measurements that would get us down to the sensitivity that we need to make such a measurement for a truly Earth-sized object. We need to shrink our error bars by just a factor of 3. And with HST, it's not possible, but JWST will let us do that. And so, but even with JWST, it'll be a similar case as now with HST. We'll be able to look at maybe one of the nearest or best possible target and get a high-quality transmission spectrum of it. And that is not enough, in my opinion, to get a robust detection of life. The planet's atmosphere could be cloudy. It could have experienced a runaway greenhouse effect and been rendered uninhabitable. It could have lost its atmosphere. There could, even if we have perfect constraints on its atmospheric composition, there could be false positive signs of life from abiotic processes. And so the next step, what we need to do, is build a ginormous space telescope, which many of you may be familiar with, as was recently suggested by the report from AURA. They recommended a 12-meter diameter UV-OIR observatory to be a follow-up to JWST. And that telescope would be capable of directly imaging a large sample of Earth-like planets and measuring spectra for those planets. And now we'd be in business, because with a large sample, we can begin to, we'll identify cloud-grade samples, we'll be able to put false positives in context, and we'll be able to explore the full diversity of atmospheric compositions, of climates, and stellar host environments. And so if I were a betting man, I would put my money on strong evidence, or one more thing, strong evidence for life. Let me close this with a meta-argument, which is the following. The history of science has held many surprises. I doubt that 30 years ago, any astronomer would have predicted that we live in an accelerating universe that is filled with planets. And the lesson I take away from this is that we should be open-minded about what we hope to expect. And I urge you to keep that in mind as you make your votes.
This is okay.
You have to point it to your mouth, otherwise.
Get close to your mouth.
So the con side.
Living planets are better than dead ones. We all hope that life is widespread in the universe. Anything else would seem like a waste of space, given that we now know there are a large number of habitable to roughly that-sized planets. But we should vote based on facts, not hopes. And the facts are that the origin of life appears to be very difficult. To be capable of Darwinian evolution, the minimum entity has several hundred atoms. The chance of that arising spontaneously from a chemical reaction is very small, and no organizing principle has been discovered that could bridge the gap between non-replicators and replicators, although Jeremy England has tried. We've known since 1859, with Pasteur's experiment, that life does not arise spontaneously in the laboratory. And all efforts since then to coax life into existence in the laboratory have failed. Every planet and every moon that we have landed on is dead. And we have samples from many dwarf planets in the asteroid belt that contain percent levels of prebiotic molecules, quite complex organic matter, and which were irrigated early in their history by water at pleasant temperatures for millions of years, and nothing happened. So both at the lab scale and at the minor planet scale, nothing happens. Of course, something happened at least once, because here we are. So it's rather sort of discomforting to think of the origin of life as an event that might have occurred only once in the observable universe. Science can't really do much with unique past events. And so you won't find many specialists in the origin of life who will admit in print that the origin of life might be a very rare event because they'd be arguing themselves out of a job. But what would a universe in which the origin of life was rare look like? Well, there'd be many large, closely connected domains with no origin of life. There would be some with one origin of life event, and there would be a few with two. And there's nothing in our biology or geology or astronomy to disfavor such a scenario. So the universe doesn't really care what makes us uncomfortable. So I've outlined two scenarios, one in which the origin of life is common, which is, or is easy, which is basically ruled out by the failure of spontaneous generation experiments, data from the asteroid belt, and the ongoing continued failure to make life in the lab. And one in which it is extremely rare, which is totally consistent with all data. Now the truth has to be extremely close on a log scale to the first option, which has been already ruled out, if the first generation of spectroscopic surveys of rocky exoplanets are to find evidence for life. And that's especially true when you consider that most biospheres will succumb to climate instability, that extremophile biospheres undetectable over interplanetary, never mind interstellar distances, and that there is no combination of oxygen, ozone, carbon dioxide, and methane that cannot be explained by geological processes as well as by biological processes. I'd like to finish by saying you shouldn't feel any cognitive dissonance in voting no. This question isn't going to be answered by a debate. It can only be answered by continued exploration. Exploration must continue. But just because you think that it's less likely, it's more likely than not that the first generation of rocky exoplanet atmospheric surveys won't find evidence for life, that doesn't mean that you're against exoplanet research. We can be good stewards of the public by investing in science that has a small chance of paying off, but would return very large rewards if it does so. And that describes a lot of science at the frontier. So don't feel any, but to vote yes, you have to think that it's more likely than not that the first few tens of stars, maybe hundreds of stars, I'm not sure, we survey, will have evidence for life. And that's not very likely. So please don't feel any cognitive dissonance in voting.
Okay, I'm going to follow that up a little bit more quantitatively. First, I'll say that historian Michael Crow of Notre Dame gave a prize lecture at the 2010 AAS, and it was called 17 Key Developments in the History of the Extraterrestrial Life Debate. So it seems relevant. When he was asked about his own opinion on the matter, he came in as a pessimist, asked why, and he said, well, because of the Fermi paradox, which he didn't list among his 17. So it's a very simple argument, and maybe academics don't want to give it all the time because it's not scholarly enough or whatever, but just because it's simple doesn't mean it's wrong. So let me walk you through it. The idea is, if aliens really are out there, then where is everybody? How come they have not visited the Earth? Not just why aren't they here now, but why are there no artifacts of those aliens? In this audience, I don't think I need to defend that proposition that there are no such artifacts. Not even a measly obelisk on the moon. All right, so The solar system's been around the galaxy 50 times since it formed, and that's just with the benefit of gravity. If you have rockets and intelligence propelling you, you can get around the galaxy much quicker than that. So this was an idea published by Hart and by Tipler, starting at that fateful 1950s lunch comment by Fermi, our Chicago hero. All right, so how does life get to the state of colonizing the galaxy? It has to go through a series of states, which are quantified in the Drake equation. But there's an argument called the Great Filter, which was discussed by Hansen and Bostrom. Step one is to have an old enough Earth-like planet. As several commenters have said, Kepler's shown us that these are very common around sun-like stars, even M-dwarfs, and so that's not a problem. One problem might be that they're not old enough. Maybe we're the oldest civilization out there, so we've got to jump on everyone. This is also ruled out because Kepler has found systems of rocky planets around a 10 gigayear star, so twice as old as us. Also, rocky planets do not care about the metallicity of their host star, unlike giant planets. So therefore, there is no longer any impetus for the galactic habitable zone, which requires galactic chemical evolution before rocky planets are formed. Therefore, we've gotten past step one. We know there's planets out there that could support life and are old enough. Now, step two is arising from simple to the point of simple replicating organisms from non-life. And you heard a variety of comments on whether that's possible. As an astronomer, I don't want to comment, but suffice it to say, I think that this is the filter. Step three, life has to go from that simple replicating state to being as advanced as us. This is overkill for creating biosignatures. Step two will get you, if you get past step two, you have biosignatures. Getting to step three is our current state. But this is the most well attested in the fossil record and by theory, the survival of the fittest. So I disagree with Dorian that this is a serious problem getting from simple molecules to us. Step four is getting from us to populating the galaxy. If you think this is a big problem, you are quite a pessimist about human nature. And also, not just human nature, but any scientific beings that arise, even robotic ones, you're quite a pessimist. And the reason is quantitative. We can do a mathematical proof by contradiction, because to decide between step two being the filter, getting from non-life to life, and step four, getting from us to populating the galaxy, one of them is probably orders of magnitude more likely than the other. So that's the great filter argument. So by 2042, we will have surveyed 100, I'll grant the opposition that we will have surveyed 100 habitable planets, and I'll give you plenty of biosignatures galore, but Jacob will take them back. And so let's say we find something. This is the proof by contradiction. We find an biosignatures gas there. That means that the great filter is ahead of us. There's approximately 1 billion, if you find 1 out of 100 with life, there's approximately 1 billion such cases that have gotten over step two in the galaxy. And none of those have gone on to populate the galaxy. So what that means is going step four from us to populating the galaxy is only less than 1 in a billion chance. So that's very pessimistic about our future odds, and I don't want to be sitting on that side of the aisle. So voting yes on your post-debate slip, you are dooming humanity to a stagnant future. And by voting yes to the future of humanity, you must vote no to biosignatures.
Well, after Edwin's Kevin Bacon moment, you guys have all seen that movie, right? A Few Good Men. That's the movie, right? These are the facts. The facts of the case are this. You know what I'm talking about? You didn't even know you were channeling Kevin Bacon. You were channeling Kevin Bacon.
Who is Kevin Bacon?
So I'm going to take a different approach. You know, I could stand here and talk about the extreme technological and engineering challenge of a large space telescope that has exquisite wavefront control that can suppress the starlight from a host star hosting an Earth-like planet, building an instrument that could take spectra, high signal to noise spectra of those planets, putting that space telescope in orbit. I could talk about that, but I'm not going to. I could talk about what it takes to interpret that spectrum, even if we took it for an Earth-like planet. The high-definition space telescope that Laura referred to won't tell us a lot of key information about those planets. We won't know much about the orbit of the planet, therefore we won't know the eccentricity. We won't know the mass of the planet, so interpreting the spectrum to make measurements of molecular mixing ratios will be very challenging. I won't talk about that. I could talk about how measuring a high-precision molecular abundance and tracing that back to life is very difficult, all the various geophysical processes that can give rise to life. But I'm not going to talk about that either. I'm going to take a pessimistic view on the nature of humans instead. This is not a very scientific argument, but the argument that I will make. The argument is this, is there's too many layers between now and this future of 2042. There's too many layers that we have to pass through to have that future realized. Because I'm actually very optimistic that if we could get the money, the scientists and the technologists and the engineers could pull it all off. But I don't think we're going to get the money. And I think we're going to stuck with a number of challenges. One of those challenges is in the field of exoplanets, agreeing on the right strategy and getting past the infighting that's plagued the field in the past. Once we clear that hurdle, we still have to convince all of you in the broader astronomical community to invest what might be the entire budget for many years into this one facility. And even if we do that, we still have to convince the public, the politicians in the US and probably abroad that this is the right thing to do. So science aside, technology aside, my pessimism about human nature suggests that we're not going to pull that off by 2042. That it's going to be the money that limits us, not our ability to do the observations or to interpret the measurements.
We have time remaining. Okay, so we have 2 minutes left. So on our con side, do we not? So
Don't add anything else.
all right, I'm the captain here. So, which is to say that the evidence is in the title of their proposition. And right now we have a very clear quantitative way to assess evidence in science, and it's the Bayesian method of statistical assessment. So we need to compare different models to explain the data and then compare them quantitatively. So if you say yes on your slip, you are saying that you have completely enumerated all the possibilities for whatever the spectra say, and that these possibilities give a decisive, according to the data, give a decisive victory to biosignatures, unique ones that are not geophysical. So consider the weight of that comment.
And a concrete example of what Dad is talking about. In the 60s, if you said there's methane in Mars's atmosphere, people would have jumped up and down and called it a biosignature. There is probably small amounts of methane in Mars's atmosphere. The discovery has been cemented by its detection in situ by the Curiosity rover. And it took roughly 3 pots of coffee and 3 graduate students to come up with half a dozen excellent abiotic explanations for the data.
Okay, so we have 30 seconds. We can go for coffee, or we can just go to the rebuttal from the pro side. So the pro side is going to have now 2 minutes to respond to the arguments of the con side.
First, I want to deal with the origin of life. So one argument that Edward made is that the origin of life is very rare because it seems to have only happened on once. Or at least that was what on Earth once. That was what I understood him to be arguing. But if life had originated multiple times, it would have immediately been outcompeted by existing life. So it's totally expected that you would only have one origin of life on a body. Second point is the Fermi paradox, which Dan was talking about. So I think he artificially excluded the possibility that life gets stuck between simple bacterial life and between technological us's. And there are 2 big barriers between that are probably low likely. low likelihood. So the first is the evolution of complex life, which we know took a really long time, 3 billion years on Earth. And so it may have been just the strange vagaries of our particular situation that allowed us to evolve complex life. And the second thing is once you have animal life, intelligent life doesn't seem to be particularly Darwinianly favorable. So, like cows are doing just fine, not building radio telescopes. And for 600 million years, animals are not building radio telescopes. And so those are really big issues for the furry paradox. So you can have, so it's very easy to imagine that you have billions of planets that have simple life and still be completely consistent with the furry paradox.
I want to rebut Jacob's point because he is my advisor and so it's my duty to do so. So I would say first that this pessimistic view about human nature is, I disagree with it because I think you're discounting both the tremendous public fascination with the search for alien life. I think there's huge interest in this that can trump some of the petty political disagreements that would prevent such a mission from being funded. And I think you're also discounting the potential of human ingenuity to develop cheaper methods for building a mission like this.
I'm just gonna leave it on. Sorry, you gotta stay on line. So now the con side gets 2-minute rebuttal.
Okay. I'd just like to make one point, which is that oxygen sucks. So the issue is that if you fertilize water, then the hydrogen escapes space quite easily. The oxygen builds up. So using oxygen as a biomarker is very tricky. And so you really do have to resort to exotica like isoprene before you can start saying, yes, this is really hard to make non-biologically. Maybe we're looking at some biology that's putting this in the atmosphere. Similar arguments apply to gases like ammonia.
Yes, it is true, Dorian, that I discounted step 3, getting to complex life from simple life, intelligent life to simple life, from simple life. And the reason is because I found a factor of 1 billion, and I couldn't imagine that I could ascribe that all to that step. This is a rare earth hypothesis that most astronomers cannot abide, in my opinion.
So Laura, I'm glad you feel like you have a future in the field. I would be really embarrassed if I convinced you to switch from, what were you going to do? It doesn't matter. I've made the pitch for, have you considered a future in the field of exoplanets so many times that I would feel like a charlatan if maybe you guys weren't right. So the truth is I actually should be sitting on the other side, but I wanted to offer my statement as an argument for the debate, but more as a challenge to all of us to make this actually happen. And so I would rather lose the debate and ultimately win the war, let's say.
10 seconds? No? Anyone want to make up for what you did? Okay, then.
So at this point, we're going to have questions from the audience, is that right?
Yes.
Did I just...
So we have about 12 minutes for questions. Please choose a side if you can for the question, but you don't have to. If it's for both sides, we'll figure it out. Yes. Do you want?
Take the mic.
Yeah.
I'll make sure that everyone has this.
There seems to be an underlying assumption that in order to make exoplanets, although there are some components, to make exoplanet research interesting, it has to be about life. People have been studying stars for centuries without any hope that discovering life on stars. Right? I think it's interesting to survey exoplanets and to study exoplanets just as astronomical objects. I understand the fascination with life, and if it comes about, that's great, but I think underlying motivation to study this is the same as to study any other object in space.
I'm glad you feel that way, and while the votes are being counted, we're going to talk about non-life subjects and exoplanets as questions to the panel.
Okay. So let me just say, we will do the post vote after the question period. I mean, it's okay to do it now. But the question period is kind of meant to sort of clarify any lingering doubts you might have one way or another. Okay, but you can do it now if you want to, but I suggest you wait till after.
Everybody already decided in favor, right?
Can I move my chair over there?
I just have a couple of comments to help each part, but you can take whatever you can for that. So first, I think Laura provided the solution to her advisor's quandary. She said she used the word Trump. So you can use your imagination on that. The two comments I wanted to make, one was people have invoked in many other contexts, also in cosmology, the anthropic principle, that we are here because it was made for us. It was made, we are here because the universe was made for us and all the multiple other universes are elsewhere. And so, in that context, which has other arguments that were brought in support, then the fact that we are alone in the universe would seem less culturally surprising. The argument for the other team is this issue of why the Fermi paradox, and some people speculated that really advanced civilization, when they really get advanced, are really non-curious for whatever reasons. They find that hunkering down is maybe a preservation method, and maybe there's some bad experiences of running into some other civilizations before, so they decided to just lie low. And so the argument is that the most advanced civilizations just are happily just not interested in visiting anywhere. So.
Does anyone want to address on that?
Yeah, I was the one arguing for the Fermi paradox. So I think there's an order of magnitude problem there, because what you're saying is out of these potentially 1 billion civilizations in the galaxy, none of them are, all of them have decided that that's the best solution. They're all going to hunker down, and none of them have visited us. So I think that's a problem.
That was maybe the Darwinian principle, that once you decided to visit, got each.
Well, we would see their obelisk at least before they went.
Next question here.
How did you decide to split yourselves up, and how many of you really wanted to be at the other table?
How did you decide to split yourselves up? And do you have to agree with the one you're arguing?
Okay, raise your hand if you agree with what you're arguing for. Two observers, two geophysicists, that was part of it.
I kind of wanted to pull a clarification on the robustness of biosignatures, because I'm not aware of this at all. But like, right, so I've heard like ammonia and oxygen as potential biomarkers, but other things can produce these things as well. So are there, say, patterns in the abundance of these signatures that would be more indicative towards evolving life, or is that just too long a span of time to follow, or what's the general direction of actually assessing the robustness of the biosignature?
Yeah, that's an excellent question, and it's an ongoing area of research. For oxygen, the false positive scenario that Edwin proposed, where you're photolysing water and the hydrogen is escaping, at least while that's happening, there are other atmospheric diagnostics that you could use to assess whether that's going on. So you could look and see if the planet atmosphere is saturated in water vapor. Similarly, you could also have oxygen build up on a dry planet with a CO2-rich atmosphere and low sinks of oxygen on the ground. But in that case, you could look and see that there's a very low mixing ratio of water, also from spectral features. So there will always be some false positive scenarios, and so we will have to do some sort of probabilistic assessment. The main small molecules that life can create in abundance are, chemical processes have the same constituent materials to work with. But oxygen and especially ammonia, which has a short photochemical lifetime, I think are two of the most robust proposals in the various scenarios.
I would just add briefly that the advantage we have of studying exoplanets is that the sample size is virtually unlimited. And so even though a single detection of a possible biosignature on one planet, I wouldn't argue is robust evidence. The sky is the limit as far as how many we can look at. And the funding agencies.
Hello. I just want to show you the numbers. You said the 1/1000th of the Earth's biomass in the oceans, the cellular biomass, you said is detectable for one planet with JWST and order hundreds of planets with the ultimate next generation space telescope?
Yeah, so this is an estimate from Seeger et al. 2013 that considered, they called these rocky planets with hydrogen atmospheres where little alien critters managed to extract energy by combining molecular hydrogen and molecular nitrogen together.
Presumably on Earth we know how much, I mean we know what kind of life we have on Earth, so we know what 1/1000th of the cellular life the Earth's ocean would produce.
Yeah, well, so this is, essentially to get that estimate, they estimated how much energy we need to get out of, how much energy can be produced by that reaction, that basic metabolism. Approximately how much energy per gram do bacteria require to just maintain themselves, kind of their basal metabolic rate, and then how much ammonium would that reveal? And so they got essentially 0.1 grams per meter cubed of bacteria if these bacteria manage to use that metabolism. And that in the ocean, there's about 10 grams per meter cubed of cyanobacteria. So it's a total, I mean, that's a minimum biomass of these nitrogen consuming bacteria. But there's still 3 orders of magnitude of buffer room for inefficiencies or sinks or other processes.
What the Earth, the solar system, to you has 2 Earth-like planets, right?
Depends on how you define it.
So I guess we were asked to choose a side, and I'm firmly on the con side. I think that's clear for me. But I had a couple of things which you all might want to comment on. So one was the thing about the Fermi paradox. And this comes up all the time. Arya said that maybe they were not curious and they were just hankering down. I think that's almost impossible. We talk about an advanced civilization, which means that it's technologically advanced. It has to be technologically advanced. Which means that they must be using energy, they must be, even just from the point of view of energy and stuff, we know our resources will run out in a couple of, I don't know, people have different opinions, but they will run out. Other planets might run out too, so people have to advance. So I don't think that they will be... Fusion. Pardon? Hopefully, well, okay, but then we're making further this thing, where would that come from? And then we've heard of Dyson spheres and things and all. So would you really believe that, you can have advanced civilizations that would not actually be curious and would not be trying to go ahead? And I want to ask one more question, because somebody mentioned about having animal life but not going on to human life. Again, I find that very hard to believe. Do you think we'd come to monkeys and then suddenly Darwinian evolution would stop and not go further on ahead and just suddenly hesitate in the middle? I guess there are lots of comments, so that's a good one.
Laura and I both have something to say. Yes. I mean, I actually don't think having intelligence is particularly useful for surviving and reproducing necessarily. And we can see that from the fact that we had hundreds of millions of years of animals that never developed the kind of intelligence you need for interstellar or interplanetary travel. And similarly, you can see that we had 3 billion years of simple life that never decided it had to get complex. So I actually see those as potentially very large barriers that could really cut down on the billion estimate that Dan was talking about.
Maybe.
So I wanted to ask both sides what you consider to be the weakest parts of your own argument.
Tomorrow, someone might come up with a convincing mechanism for a relatively straightforward origin of life. So the weakest point of diagnosis is predicated on 150 years of lots of smart people trying something and failing.
Just that the unpredictability of the future.
My argument was really a ploy to get everybody on board with,
Yeah, so I would say it's the biggest weakness is false positives, biosignature false positives.
False positive.
Agreed, and I should also mention, Jacob touched on this, that the measurements we're proposing are extraordinarily difficult. To be able to directly image and reflect planet, you have to achieve a contrast ratio of 10 to the 10 at a separation of 35 milliards seconds. And so even with a huge amount of money and ingenuity and time spent, it will be very challenging to do.
Will it be a lot harder, assuming that we find out, to detect simple life rather than complex life?
Well, okay. So about false positives, thanks for going today. About false positives, it'd be pretty hard to have a false positive if we get a radio signature, from an intelligent life, right? So if we get intelligent life, there are certain ways where we'll pretty much eliminate false positives. But if you're just looking at the gases in an atmosphere, it's not particularly harder to detect bacteria, or humans or bacteria. Neither one is
So 2 billion-year-old Earth would have been just as easy to detect as the rest of the Earth.
Well, one difference is that oxygenic photosynthesis, and the oxygen level in the atmosphere was significantly lower at 2 billion years ago. So there would be differences, but yes. What? Oxygen? Probably not. 100,000 times lower.
I'm going to go back down to this side.
Good? Are we set? All right. So before you vote on the blue paper, it's my duty to remind you what the question actually was. Okay? So I know you can read, but by the end of 2042, 25 years, not ever, just 25 years, remote sensing will reveal evidence of extant life on an exoplanet. Okay, so please cast your votes again, and we'll pick them up and count them.
That's supposed to be decisive evidence or just evidence?
That would be
Okay, so in the meantime, if while we're counting these other votes, we have a few minutes during which we can take a few more questions. And I recommend stepping away from the topic of life. Anything on exoplanets goes, and to either side or both sides together. Okay?
Sorry, I'm going to ask a question about life. So do you think that UChicago should have people who are focusing on these questions you were talking about today, have sort of like an astrobiology type of department? Do you think that's something that would be worthwhile here in Chicago?
I'd say you're looking at it in a way, and that all of us here, this is part of the reason why this panel spans not just our astronomy and astrophysics department, which has been the central theme of today's meeting, but also includes our colleagues from the geophysical sciences department, because this is a topic that we're using to build a bridge between these two departments, and that we have built up a fairly substantial group just over the last few years, astronomers working on the detection and characterization theory of exoplanets, geophysical sciences working on the study of the planets in our own solar system and applying what we've learned about those planets to exoplanets. So I'd say we're going in that direction, I think, for sure.
So do we have like a sort of formal group, or do you think that's something that should be pushed forward? Do you already have that?
No, we don't have a traditional, as far as this tradition, astrobiology program like we have at the University of Washington State. I think we could cast the net broader and get more chemists and whatnot on board. We do have a much broader range than what you see up here. This is more of the astronomy side of it. Jake Waldbauer and others are just off of the stage here, could have been invited for that. So yeah, we're pretty deep.
We did actually try to do this. 5 years ago we tried, and NASA turned us down.
So is it possible to get any of these biosignatures with a 30-meter scale telescopes? And if not, how would we convince the whole community to spend money on the next space-based mission when we need from Lisa?
Yeah, that was exactly my point. So I think most of us are focused on what we would do with a very large space telescope in the area of direct imaging. We kind of glossed over what you could do in the area of transit spectroscopy. Laura did touch on that with Steve, but with the caveat that maybe we'll only do a couple planets. One thing that has totally not been mentioned is what we would do, for example, with the Giant Magellan Telescope. And I mentioned this earlier, but didn't go into a lot of detail. But the idea of looking not at low resolution spectra, but at very high resolution spectra. I'm talking about resolution resolving powers of 100,000 or 150,000, something like that. And there is the possibility, I think, of looking in transiting planets, this would be planets orbiting M dwarfs if we're talking about habitable zone planets, of doing high resolution near infrared and optical spectroscopy to resolve, say, the molecular oxygen, the band that you see around 800 nanometers in our own Earth's atmosphere, taking advantage of the Doppler velocity shift because the planet's orbiting another star and the star's having some sort of red or blue shift relative to us. So that is possible, but it's a lot more uncertain. A lot of the emphasis on detecting biosignatures has been in the direct imaging game because people have been talking about that for almost 20 years now. And so this area of high resolution spectroscopy is less explored, but also still promising.
I just want to say it's not necessarily a zero-sum game. Like there's N dollars and it either goes to one thing or the other. So we know that exoplanets are generating huge excitement, and if you potentially build a big exoplanet instrument and make a light detection, that could just lead to more money going to astronomy in general. And the second thing is the HDST, which is, did I get the acronym right? Yeah, this thing is not just a like exoplanet light detector. There's all sorts of astronomy that it could be used for.
This is a question for Edwin and possibly others. You talk about failure to build up from simple molecules to the simplest organisms. Is there any history of going in the other direction, taking the simplest organisms that exist now and ablating them or simplifying them further and seeing if they survive?
Yes, it dies when it's still a few hundred genes, so still ridiculously complicated. So bottom up is more likely to succeed. So these sort of minimal organisms you're talking about, I mean, you can get them commercially because they're used by so many groups, but they're several hundred genes.
I had a question about the radio searches for extraterrestrial life. So I know kind of historically it feels like to me that that was a big topic a couple decades ago and kind of died off, and kind of the interest in life has kind of renewed, I guess, with exoplanets. So for those on the panel, what do you see as future using radio waves again to look for life in the universe? And perhaps you heard us to talk about future 21 centimeter experiments. Is that a window that people use for new radio experiments to look for life?
Let me just say briefly that a really rich Russian dude just donated $100 million to SETI. And you're right that it had kind of died out, and I think that it's most promising to look for biosignatures in the atmospheres of planets, but there's been, as you say, renewed interest in searching for radio signals, and so it's still funded and operating and complementary to what we're
voted for finding life, but intelligent life, as we know, we descend from the monkeys and still descending. I don't think we will survive long enough to detect life anywhere else, any intelligent life anywhere else.
bomb, but we didn't do it, right? We're here.
There's this exhibit right here.
I know, look for the exhibit.
Nuclear missiles are on alert now.
Do you mind if we end on a positive note? We're waiting for the post votes, but I can certainly announce the results of the pre-vote now. Okay. So remember, these are going into the time capsule. So it's a good thing you didn't sign your name on it. Okay. All right. So the pre-debate votes are 33 against the question, so not thinking that life will be found by 2042, and 38 yes. Okay. So let's see what happens post-debate.
How about we just do this really quick? Raise your hand if you changed your vote. Raise your hand if you changed from yes to no. You changed from yes to no. No to yes. I think this means that we won. There were certainly more people that changed. So I mean, it was slightly in favor of. It was slightly. You know the answer. That tells us the answer right there. We don't have to count it. It was slightly in favor of yes beforehand, and then slightly in favor of no. To shift from yes to no. So I would say it probably came out very even. We don't even do 1% cosmology precision on this vote. Chad, how many hanging chads died earlier? It's 5 o'clock, so I would say not like it.
And you just put up your hands now, I know. Yeah, right, I think. There come,
here they come.
The post-debate votes. Okay. Okay, so again, the pre-debate votes for 38 yes and 33 no, and the post-debate votes are 38 yes and 40 no.
Alright, I think we are following the Chicago tradition of voting often. And I will declare that this was even, okay? With an error. Let's thank everybody. Thank everybody for this wonderful debate for the whole day, and now we can celebrate upstairs. Everybody's invited to our 5th floor to have some food and drinks.